Hello everyone. Today, we are excited to present our work titled Probabilistic Triangulation for Uncalibrated Multiview 3D Human Pose Estimation. This paper introduces a probabilistic triangulation module that can be seamlessly integrated into calibrated 3D human pose estimation methods, extending their applicability to uncalibrated scenes. 3D human pose estimation is a fundamental tool in numerous computer vision and computer graphics applications, with multiview methods consistently delivering superior precision compared to other approaches. So, how do we reconstruct 3D human pose based on multiview 2D human pose estimation? It relies on the geometric relationships between projections from multiple cameras, a technique known as triangulation. Multiview methods begin by estimating 2D human body poses from each viewpoint and then, using camera poses, establish connections between these views in 3D space, ultimately solving for the 3D human pose by considering geometric constraints across various perspectives. However, existing multiview methods are constrained by the requirement for calibrated camera poses, limiting their adaptability. Our goal is to eliminate the need for known camera poses in 3D human pose estimation, thereby enabling the widespread adoption of multiview methods. When camera poses transition from known quantities to variables, we encounter a challenging shift from single-objective optimization to multi-objective optimization. Firstly, if we employ an iterative approach to optimize both camera poses and X3D alternately, the results often converge to local optima. Secondly, if we use a neural network to predict Y and subsequently solve for X3D, it may struggle due to the limited diversity in the existing training dataset. Thirdly, if a neural network is used to directly regress X3D from a monocular view and then solve for Y, it introduces the issue of monocular scale ambiguity. In summary, we must extract more information from the only known quantity, X2D, to obtain a relatively accurate estimate of Y, such as its posterior probability. As illustrated in the figure, this is a calibrated 3D human pose estimation algorithm where camera poses are applied between 2D pose estimation and 3D pose reconstruction to establish the connection between 2D and 3D heat maps. We propose a probabilistic triangulation module that updates and maintains estimates of the camera pose distribution instead of relying on the camera pose itself, thus eliminating the need for camera calibration. Specifically, we perform iterative Monte Carlo sampling, computing each sampled camera parameter through reprojection to obtain an explicit approximation of the 3D heat map. The 3D heat map calculates the weights of the sampled camera parameters, which are subsequently used to update the pose distribution of the cameras. Regarding the details of computing the posterior distribution, when we expand the target problem of reprojection error, it transforms into an unsolvable original problem. To address this, we introduce an explicit discrete approximation of the 3D heat map, thus converting the problem into one that can be approximately solved. Based on this transformed optimization problem, we can calculate the posterior probability for each sample and adjust the camera distribution Q accordingly. The visualization in the figure displays sampled points in 4 iterations after dimensionality reduction using T-SEN-E. From left to right, it corresponds to the sampled values after 4 iterations. A smaller value indicates that the sampled point is closer to the true value, while the logarithmic sampling loss represents the value of the sampled point relative to the true value. The experimental results demonstrate that our method's mean per joint position error outperforms state-of-the-art uncalibrated approaches and achieves performance comparable to calibrated methods in 3D human pose estimation. In experiments related to camera pose estimation results, probabilistic triangulation also outperforms traditional camera pose estimation methods in this specific context. Finally, we further demonstrate and analyze the performance of probabilistic triangulation through cross-dataset experiments, variations in camera quantities, and ablation studies. We sincerely appreciate your attentive audience.